Our first organometallic reagent is an organolithiate. So we have an organic species and it's attached to a lithium. How do we make those? We make those by mixing alkyl halides with lithium metal. So lithium 0. What does that 0 mean again? Think about that. It's not charged. So it means it's in its elemental form. So where is lithium on a periodic table? And is it very stable like that? What does lithium want to do to become stable? So you should look at a periodic table right now. Look at where is lithium? What can it do to gain an octet? And you've done that. And what you see is that lithium is all the way in group 1, which means lithium has 1 valence electron. So how can it gain an octet? It can gain an octet by giving up an electron. So how is this going to react with an alkyl bromide? Well, lithium, we'll just draw it like this, lithium with 1 valence electron is actually going to react with this alkyl halide in a radical mechanism. So essentially it's going to give away its electron, it's getting rid of it. That is going to combine with a bromine, and then that carbon-bromine bond is breaking, meaning that we have a carbon radical plus lithium gave away its electron, so what is its charge now? Yeah, it is positively charged, and then bromine gained an electron. What does that mean? Bromine is negatively charged. So we have lithium gains an octet, bromine gains an octet. What else do we have? We have a really unstable carbon radical. How can that gain an octet? Well, we have more lithium metal around. We have more lithium 0, which again I'm going to draw just as a radical here. That is going to combine with the carbon radical to make our organolithiate, which again sometimes we draw with a full carbon-carbon bond in a covalent fashion, but also it's totally acceptable to draw this, and I think that it's actually more indicative of its chemical character as that covalent bond, because it really, as that ionic bond, because it really shows that this must be a really reactive species, and that carbon must be really nucleophilic, and that's really going to come into play soon. So let's fill in our blanks at the bottom of a page. All right, here's our first blank. So unstable elemental lithium gains an blank. It's got to start with the vowel, right? And becoming stable. So elemental lithium gains an octet. It gave up an electron, and that gave it an octet, which made it stable. So that's how this reaction, we always say reactions go downhill, making more stable species than what we started with. We're making a really stable salt. We're making an unstable organometallic, but in that process, a lot of things are gaining an octet, which is why these organolithiates can be synthesized. All right, we're on to our next blank now. While working with reactive organometallic reagents, solvents lacking any blank must be used. So think back to what we talked about with lithium aluminum hydride. That was a really reactive species, and those hydrides would pull protons off of the solvent if they were available. So solvents lacking any acidic protons must be used. So what did we use for lithium aluminum hydride? We used ethereal solvents, so ethers. Tetrahydrofuran was that cyclic ether. Diethyl ether was the other ether. And we had to use those because that lithium aluminum hydride would just pull the proton off of the solvent. Same thing goes for acetylide ions. Acetylide ions, again, will do acid-base chemistry, and these organometallic reagents are even more reactive than an acetylide ion, so obviously they are also going to pull protons off of solvent molecules. So for instance, if we had the organolithiate that is on your page, mixed with some protic solvent like this methanol, what's going to happen? Well, the pKa of methanol is, 16. So if this bond is going to it really belongs to that carbon, so this arrow indicates that that carbon is grabbing that proton, and then that is breaking just in the standard acid-base reaction. That would generate this carbon-hydrogen bond plus lithium methoxide. So what side is going to be favored here? Well, what's the pKa of this proton? CH4 was 50. This kind of looks similar-ish to an sp2 hybridized carbon-hydrogen bond, which is 44 based on your pKa table. So which side is favored? This is a much stronger acid, so anytime we have an organometallic mixed with acidic protons, acid-base chemistry is going to occur. So that just brings me to want to write up here that organometallic, so I'm just going to write CMs, are super reactive, right? So they are nucleophilic, and, this is a big and, they are basic. So if we have any acidic protons, they will grab those protons. More on that later. All right, so for an example, I want to bring your eyes to the top. Organolithiates react like acetylide ions do. So what is going to be made here? Note we have two reagents. We have one and we have two. So there's clearly going to be a box down here that you would need to fill in. And then we would react with the second reagent and we would make the product. So fill in those boxes. Draw some extra arrows if you want to. As far as how this relates to what's on the class notes, phenyl, remember, is a benzene ring. So on the notes, it says it has the full benzene ring with the lithium. Here I just have the pH. So fill in those boxes and take a stab at this blank here too. So do that right now. Okay, you've done that. Okay, so these react just like acetylide ions. Again, phenylithium is part covalent, part ionic. Sometimes it helps to show it as the ion. So phenyl negative with the lone pair and lithium plus. So here's our negative nucleophile. Where's that going to go? That's going to be attracted to the most partially positive thing in the reaction, which is that carbonyl carbon. So those electrons would add up there. That would make new carbon-carbon bond, and our intermediate here would have that added in there. Now I want to get down to this blank. When stereoisomers are present, nucleophilic addition with organometallics, RMs, makes, what did it make when it was hydride reagents? All configurations, right? All configurations. Is there any reason why the lithiate, the phenyl anion would add just from the front or just from the back? No, it's going to add both ways indiscriminately, right? It's going to add both ways. So we can draw that with, essentially we'll put our O minus here, and then we'll draw that squiggly guy to the phenyl, which indicates that that squiggle is a mixture of the wedge and the dash. So that's the intermediate that we have here. Did we go downhill? Yes, we went very far downhill. An O anion is much more stable than a C anion. What happens in reaction 2? We have our acid present. We have the oxygen anion, which is somewhat basic. That is going to come and grab that proton and generate our product, which is an alcohol. And it doesn't matter if we have the squiggle to the O or to the pH. If we just have one of the two, it indicates that it's both types of stereoisomers, both the R and the S. So that's how you would have worked through that one. So that is kind of all the stuff about organolithiates, how they react. So, yeah.